All right, hello guys. I have one more section to pre-record for you for Wednesday. This is section 4.8, the surge function and drug growth. Applications of derivatives in medicine happen a lot. We generally use them to find out how people will metabolize medicine in their bloodstream. It's used to predict like how much is in their bloodstream at a given time, and then when another dose might be appropriate, how high or how low the concentration of that dose should be. So our first example here, we're going to look at, and I wanted to list up here, this is the surge function in standard form, where both A and this B value are really important, and this B value in particular is really important. They are both positive constants. Okay, so let's look at an example of a surge function. Here they're saying that when a person smokes a cigarette, the nicotine from the cigarette enters the body through the lungs, is absorbed into the blood and spreads throughout the body. The nicotine level in the blood rises as a person smokes and tapers off when smoking ceases or when they stop. The table shows blood nicotine concentration in this unit of measure during and after the use of cigarettes. So first question is, how many minutes does it take to reach peak concentration, and what is the concentration at that time? First, let's take a look at what's really happening, right? If you smoke a cigarette, it's going to take you about 10 minutes at the most, right? So this is when you are, I should say, actively smoking. Right, from zero, I shouldn't circle that. But notice, after 10 minutes, you're not smoking a cigarette anymore, but the level of nicotine just tapers off, right? So when you're actively smoking, notice how it goes up from 4 to 12 to 17, and then starts to decrease. So if I'm going to ask you how many minutes does it take to reach peak concentration, well, the peak concentration is going to be the highest value, right? So this is the peak concentration. Right here. But to answer the when, how many minutes, you're gonna answer that by looking at the t values. So the t value there is about 10 minutes. And the concentration at that level would be the y value here, right? And that's at about 17. This unit of measure. So this section is really about reading the graph. There's a little bit of derivatives in this section, but it's really about reading the graphs. So first we have different parameters. I told you the B parameter in the original function up here is important. So let's see, I'm going to have to move this down a little bit. All right, so it says it's giving you this graph. They don't put the A in front of the T, but that's okay. It's sort of implied that it could have a coefficient there. So it's still the same thing. They're still talking about the standard form of a surge function. So it says The graphs of that surge function for different positive values of B are in this figure below here. The general shape of the curve will not change as B changes. So the general shape is going to stay the same. But what's important here is that as, oops, let me get my pen. As B decreases, the curve is going to rise for a longer period of time and to a higher value. So B is large for this graph, right? And notice it's kind of short. And as B gets larger, B is larger here in this curve, and notice that it's much taller. All right. In this figure, when B is equal to 1, the max occurs about T is equal to 1, right? So I'm looking at the highest point of that graph, and that occurs after T is 1, say 1 day, right? Or 1 hour probably is more appropriate for drugs. And then if you look here, about the top of that aligns with that 1/2, and the top of this aligns with this. So we're talking about this B value, we're talking about the B value that's in this standard formula for surge functions, which makes it easy because you can say that the max is going to occur at 1 over whatever B is, right? So here, for B is greater than 0, show that the maximum value occurs at 1 over B. So really, this is just a proof for what we already know right here. Okay, so let's take the standard function y is equal to t e to the negative bt. And we're just going to prove that this actually does work. So if we call this our f and this our g, what we're going to do to find the max, like we did in another section, is set the first derivative equal to 0 and solve. And when we solve, we should get 1 over b. So let's see if we do. Let me move this down a little bit. Okay, so of course we're going to use the product rule. So we have f prime g plus f g prime. So f prime would just be 1 because the derivative of t is just 1, and g is just e to the negative bt. And f by itself is just t. And g prime, we're going to use this rule that says that the derivative of e to the kt power is equal to, actually, I don't want to use t, I don't want to confuse you. X power is equal to x e to the kx. Okay. So we've got t, and then the derivative of e to the negative bt would just be negative b would come up front, e to the negative bt. So let's see, let's write that a little more interesting, or a little more simply. E to the negative bt, oops, this would be minus. This would be minus et e to the negative bt. And then of course you can factor out e to the negative bt to get that times 1 minus bt. And now I can set that equal to 0 and solve for t. So if you divide both sides by e to the negative bt, you can get rid of it because anything that you divide 0 by is just going to be 0. So now we're left with this real simple 1 minus bt is equal to 0. So if you solve that for t, you will get, let's see, t is equal to 1 over b. So what we just did is we showed that the maximum value of y equals t e to the negative bt power does occur at t is equal to 1 over b, because that's how you find the maximum. You set the derivative equal to 0 and solve for the variable. And the second part of this is asking, I'm going to need more room. The second part of this is asking, let's look at it here. So this is, we showed that the maximum value occurs at 1 over b, right? Right there. And then we also want to show that it increases as b increases. So you can do that by starting out with the formula again. Y is equal to t e to the negative bt. And then since we know that t is equal to 1 over b, we can plug that in. So y equals 1 over b e to the negative bt power. Oh, sorry. We got to substitute it in both t's. So we're also going to substitute it. Oops, I want to do it another color. Here for t. So these are going to cancel out. So you'll just have e to the negative 1 on top. So we can say y is equal to e to the negative 1 all over b. Now, the reason why that shows that it increases as b decreases, what we know about fractions are as denominators get bigger, the whole number will get smaller, or y will get smaller. Okay, just a few more examples. This is kind of a small section. A lot of the questions on WILA, I went over all of them before I made this video just to make sure that you would be ready. But most of the questions you're going to be answering just by looking at graphs. And it's sort of simpler, right, to figure out where the max is if you're giving a graph, right? So for example, the peak concentration occurs here, right, after 1 t, and the concentration would be here. So the surge function itself is basically just a function that will increase. Oops, it increases rapidly, right? That's here. And then decreases towards zero with a minimum, or excuse me, with a max, I don't want to undo that, then decreases towards zero. So that would be, that's not a different color, shoot, not different enough. Let me get it. Let's make that just so you can really see it. Okay, and then it's going to decrease towards zero. That's this part. Here it's rapidly increasing, that's that part. And then decreasing towards zero. And this is important, and this will save you a ton of time, is that what we know already is that the max will occur when T is 1 over B. Because look at what we just did over here. We use the product rule to say that the max is going to occur here at T is equal to 1 over B, right? So that saves you time if they give you enough information in a problem, rather than differentiating it and setting that equal to 0. You can just, if you know the B value, you know that it's just going to be 1 over B. And I'll show you an example of that in a minute. Okay, so here's here a very interesting case here. So this shows drug concentrations for really it's acetaminophen, but they have this funky name for it. But this is just that the drug, we'll call it para all alone, right? So this is the peak concentration of it, right? And it happens around here, like what is that, like 22, right? And that happens maybe after an hour and a half, right? So first thing I want to compare is, let's compare the paradrug in somebody that is a normal patient to the paradrug of somebody who has slower absorption. Okay, so let's just first talk about that. If you look at it, it takes about the same amount of time, right? So para absorption is the same as normal patient, but the max concentration is much lower. For us, for a patient that has slow absorption. Okay. So here the absorption here is up here in like the 22 range, right? But with somebody with slow absorption, they're only here at like the 12 range. All right, let's look at something else now. Oops. Okay. All right, and then next, I want to take a look at, trying to use different colors. I want to look at this paragraph compared to the dotted line. Okay, so a lot of times what doctors do is they'll prescribe two different kind of medications and one medication will be the actual medication and the other medication will be something that will help generally somebody with like diabetes or some underlying thing, or an older person generally, right? Generally older people, particularly if they're overweight, will have slow absorption. So if you look at the para in this figure compared to the para with the other drug, what happens here is that if you take the other drug, it's going to take twice as long because it's going to take 3 hours, right? As opposed to 1.5 hours. So will take twice as long, 2 times. We'll take 2 times the time to reach its peak. And that might be, a doctor might put that together with the normal para to slow down the absorption. Let's say like in a young infant or somebody that they weren't sure how the drug was going to react with them, or if they were going to, have adverse reactions. So that could happen too. And then finally, if you compare the second diagram, I'll use one more color for this one. Green. Okay, so now if we compare this graph, the para with this drug that will help it be absorbed quicker with just the para drug alone in somebody that is a slow absorption kind of person, what you find is that the peak is reached faster, right? So this drug helps reach peak absorption sooner. So it's really, like I said, it's just it's reading the graphs, right? And I guess we could name some of these points. Let's see. This is like here, 1.5 hours and 23 concentration, or what did I say, 22? Whereas this peak right here, we're talking 3 hours. And for some reason, the doctors wanted to slow things down, I guess, right? And then somewhere around, what, like 16 absorption. And then this is about a half an hour and 17 absorption. And this would be like 1.5 hours. So think if you were waiting, for a drug to get into your system, to absorb it so that it could help you, the difference between a half an hour and an hour and a half could be really important to you. And this is about, what we say, 12. So they're just, the Wiley questions are just going to ask you questions, and just make sure you understand what the peak is and the Y value that goes with it, and you shouldn't have any issue with this section. All right, what's next? Okay, so minimum effective concentration. Says the minimum effective concentration of a drug is the blood concentration necessary to achieve a pharmacological response. The time at which the concentration is reached is referred to as onset, which is right here. So here's onset, and termination occurs when the drug falls below this level. So this is what's going on here. right, so here is termination over here. Oh, there's something here too. Okay, so we know that there is a minimum level of every drug of what you're going to be able to get some results from. So that would be here. When is the drug effective? It's I want to use a different color. The drug is going to be effective at all of these values, right? Those are acceptable ranges because they're above the minimum. And where is that in duration? It's here. It's all of these T values. Let's do an example of that. Well, actually, okay. So here's an example. So Depo-Provera was approved for use in the United States in 1992 as a contraceptive. Figure shows the drug concentration curve for a dose of 150 milligrams given intramuscularity. And then it goes on to say the minimum effective concentration is about 4. So let's draw a line at about 4. Minimum effective concentration is about 4. How often should the drug be administered? Well, I'm going to draw a better line than that. Let's see if that's 5. 4 is just below it. That's not the line I want. There we go. Okay, so what we know then is we know that the drug is effective anywhere above that minimum line, right? Right there. So that would be the effectiveness, the duration effectiveness would be 4 months. All right, so how often should the drug be administered? And when should the next dose be given? You want, if the minimum effective concentration would be every 4 months, right? So since the duration effectiveness is 4 months, the minimum I'm trying to say here. Oh, how often? Sorry, the minimum that the drug should be administered is every 4 months. All right, I'm thinking about a question that was on Wiley. Maybe I can look it up. Because they're saying like, so if this was every 4 months, then that would be maybe just effective, but if they overlapped it a little bit, it would be even more effective, right? But one of the questions gives you a graph kind of like this and says, what is it? It's a little bit tricky question. Let me look it up while we're online here. Okay, so it says, when should the second dose be given if the doses are to be as far apart as possible while still maintaining effectiveness? So the graph looks something like, I'm going to tell you what number this is. Oops. The graph, this is number 4.8, number 1. The graph looks something like this. Where this is the minimum level. So it says, so the minimum effective concentration shown by the dotted line. When should the second dose be given? Right, and this is 70, and this is 10. It says, when should the second dose be given if the doses are to be as far apart as possible while still maintaining effectiveness? And you would think it would be 70 minus 60, but it's actually at 70, right? Because if it stops being effective right there, then you should give it to him at 70. You should give them to him at that time because it stops being effective there. So careful with that one. All right, that is the end of 4.8. Like I said before, if you guys have trouble with this after watching the video, I can definitely meet with you, but probably not until Thursday morning of next week. So I'm gonna write an email to everybody and let them know that I won't be present for class, but you guys can use these videos to take notes and then try problems. All right, have a good one, guys. Bye.